Webb just revealed something massive, something that throws our entire understanding of the early universe into question. We thought we knew how galaxies formed back then. We had beautiful simulations, elegant theories. Turns out, wrong. The James Webb Space Telescope has found galaxies that are far too massive, far too early in the universe's history to fit any existing model. It's like finding fully grown adults where there should only be babies. What does this mean for cosmology? The data reveals a universe far stranger and more complex than we ever imagined. 700 million years. That's the time frame. 700 million years after the Big Bang, these galaxies shouldn't exist. At least, not in the form Webb is seeing them. Consider our existing models. We have simulations running on the most powerful supercomputers, painstakingly built on decades of observations. These models predict how dark matter coalesces, how gas collapses, and how stars ignite within nascent galaxies. The problem? They all agree on one thing. Galaxy formation is a gradual process. Small clumps merge, grow, and slowly evolve into the majestic spiral and elliptical galaxies we see around us today. But Webb is showing us something completely different. It's finding fully formed, massive galaxies, practically overnight. Galaxies with mature stellar populations and well-defined structures, all crammed into a cosmic epoch when they simply shouldn't be there. It's like finding a redwood forest sprouting from freshly cooled lava. The timescales are just wrong. Now, when astronomers say massive, we're not talking about something marginally larger than expected. We're talking about galaxies that rival the Milky Way in size and mass, appearing just a few 100 million years after the universe began. Remember, the Milky Way took billions of years to assemble. These early galaxies are essentially cosmic teenagers with the physique of seasoned bodybuilders. One particularly perplexing example is a galaxy affectionately nicknamed Glass Z13. This galaxy appears to have existed only 300 million years after the Big Bang, making it one of the oldest and most distant galaxies ever observed. While its exact mass is still being debated, initial estimates suggest it's far more massive than anything our models predicted for that era. Then there are the galaxies discovered in the CEERS, Cosmic Evolution Early Release Science Survey. These galaxies, observed at redshifts corresponding to roughly 500 to 700 million years after the Big Bang, are also surprisingly bright and massive. They're churning out stars at an astonishing rate, far exceeding what we thought was possible in such young galaxies. The implications are profound. These early galaxies challenge our understanding of dark matter halos, the invisible scaffolding upon which galaxies are thought to form. Our current models suggest that dark matter halos of sufficient mass to host these. Behemoth galaxies simply didn't exist that early in the universe. So how did these galaxies manage to grow so big, so fast? That's the million-dollar question. One possibility is that our understanding of star formation in the early universe is incomplete. Perhaps stars formed much more efficiently in these early galaxies, converting gas into stars at a breakneck pace. Another possibility is that the initial conditions of the universe were different than we currently assume. Maybe there were regions of higher density where dark matter and gas clumped together more quickly, accelerating galaxy formation. Or perhaps there are exotic physics at play, forces or particles we haven't yet accounted for in our models. It's also possible that these galaxies are not as massive as they appear. Their brightness could be amplified by gravitational lensing, where the gravity of a massive object in the foreground bends and magnifies the light from a more distant object. However, even after accounting for potential lensing effects, these galaxies remain remarkably massive and luminous. The James Webb Space Telescope is still relatively new, and these are early results. More observations are needed to confirm these findings and to better characterize the properties of these early galaxies. But one thing is clear: Webb is forcing us to rethink our fundamental assumptions about galaxy formation. Here's what's wild. If these early massive galaxies are indeed as abundant as the initial Webb data suggests, then our entire cosmological framework may need a serious overhaul. We may need to revise our understanding of dark matter, star formation, or even the fundamental laws of physics that govern the universe. These early galaxies aren't just a minor tweak to our existing models. They represent a fundamental challenge to our understanding of the cosmos. They suggest that the early universe was a far more dynamic and complex place than we ever imagined, and they highlight the power of new telescopes like Webb to revolutionize our understanding of the universe. Scientists discovered something else unexpected too, something that could rewrite how we understand black holes. Ever wonder if the universe is older than we think? Because the early galaxies Webb is seeing pose a huge problem for our understanding of cosmic time. See, our current cosmological models are built on the idea of a universe that's roughly 13.8 billion years old. We've used observations of the cosmic microwave background, the expansion rate of the universe, and the distribution of matter to arrive at this age. It's a well-supported framework, but these early galaxies are throwing a wrench into the gears. The issue is that these galaxies appear to be far too massive and mature for their age. They formed just a few 100 million years after the Big Bang, a cosmic blink of an eye. According to our current models, it shouldn't have been possible for galaxies of this size to assemble so quickly. There simply wasn't enough time. Think about it like this. Imagine trying to build a skyscraper in a matter of weeks. You'd need an incredibly efficient construction process, a massive workforce, and a readily available supply of materials. Similarly, these early galaxies would have required an unprecedented rate of star formation and a rapid accumulation of matter to reach their observed sizes in such a short time. This discrepancy raises a fundamental question. Are we miscalculating the ages of these galaxies? Or is our understanding of the universe's timeline fundamentally flawed? One possibility is that our methods for determining the ages of these early galaxies are inaccurate. We rely on measuring the redshifts of their light, which tells us how much the universe has expanded since the light was emitted. However, there could be systematic errors in these measurements, or perhaps the early universe had a more complex expansion history than we currently assume. It's a long shot, but worth considering. Another possibility is that the universe is actually older than we think. If the universe were, say, 15 or 16 billion years old, it would give these early galaxies more time to form. However, this would also require us to revise our understanding of the cosmic microwave background and the expansion rate of the universe, which are tightly constrained by observations. Changing those would be complicated. Scientists discovered something else about these galaxies that makes everything even more strange. Further examination revealed that many of these early galaxies contain supermassive black holes at their centers. These black holes are millions or even billions of times more massive than our Sun, and they're actively accreting matter, emitting vast amounts of energy in the process. The presence of these supermassive black holes in the early universe is another major puzzle. According to our current models, black holes grow over time by merging with other black holes and by accreting gas and dust. But it's difficult to explain how these black holes could have grown so large so quickly in the early universe. One possibility is that black holes form directly from the collapse of massive gas clouds, bypassing the need for smaller seed black holes to merge and grow. This direct collapse scenario is theoretically possible, but it requires very specific conditions that may not have been common in the early universe. Another possibility is that the growth of black holes in the early universe was fueled by an exceptionally high rate of gas accretion. Perhaps these early galaxies were bathed in a dense soup of gas, which allowed their central black holes to grow at an exponential rate. Measurements showed that these black holes are more massive than we would expect, given the size of the galaxies they inhabit. In the local universe, there's a well-established correlation between the mass of a galaxy's central black hole and the mass of its host galaxy. But these early galaxies appear to deviate from this relationship, with black holes that are significantly larger than expected. This suggests that the growth of black holes and galaxies in the early universe may have been decoupled, with black holes growing much faster than their host galaxies. This could have implications for our understanding of how galaxies and black holes co-evolve over cosmic time. The implications extend beyond just galaxy formation. These early supermassive black holes could also have played a significant role in shaping the evolution of the early universe. Their intense radiation and powerful outflows could have influenced the formation of stars and the distribution of gas in their host galaxies. They could also have contributed to the Ryanization of the universe, a crucial event in cosmic history when the intergalactic medium was transformed from a neutral to an ionized state. Here's what's wild. The existence of these early, supermassive black holes challenges our understanding of how black holes form and grow, and it suggests that the early universe was a far more violent and dynamic place than we ever imagined. Scientists discovered that these galaxies are incredibly compact. The analysis continued, revealing that these early galaxies are not only massive and mature, but also surprisingly compact. They're much smaller in size than galaxies of similar mass in the local universe. This means that the stars in these early galaxies are packed much more densely than in galaxies like our own Milky Way. This compactness could be related to the rapid star formation rates observed in these galaxies. If stars are forming at a very high rate, they could compress the surrounding gas and dust, leading to a more compact structure. It could also be a result of the way these galaxies formed, perhaps through the merger of smaller, dense clumps of matter. And then, the universe may have just been more compact. Overall, the data reveals that this compactness has some major implications. The dense stellar environment in these early galaxies could have led to more frequent stellar collisions and mergers, which could have accelerated the formation of massive stars and black holes. It could also have influenced the dynamics of the gas and dust in these galaxies, leading to more efficient star formation and the growth of supermassive black holes. This kept me up last night. If the James Webb data is accurate and all indications suggest it is, then some pretty fundamental pieces of the standard model of cosmology might need some serious re-evaluation. I'm talking about the very mechanisms that govern how we think the universe evolved. It's not just tweaking a few parameters here and there, it could mean rethinking the whole darn thing. The standard model, for those unfamiliar, is basically the bedrock of our understanding of the universe. It's a comprehensive framework that incorporates the Big Bang Theory, inflation, dark matter, dark energy, and all the processes of structure formation. It explains how the universe expanded from an incredibly hot, dense state to the vast, complex cosmos we observe today. It's been remarkably successful at predicting and explaining a wide range of cosmological phenomena. But, and this is a big but, the James Webb Space Telescope is throwing some major curveballs. The existence of these massive mature galaxies and supermassive black holes so early in the universe's history doesn't quite fit the predictions of the standard model. It's like finding fully grown oak trees sprouting just days after the Big Bang. It simply doesn't compute with our current understanding of how long it takes for such structures to form. So, what's the problem? Let's examine a few key areas where the Webb data is causing some serious head-scratching. First, galaxy formation. The standard model suggests that galaxies form gradually through the hierarchical merging of smaller structures. Small clumps of dark matter attract gas, which then cools and collapses to form stars. These small galaxies then merge together over billions of years to form larger galaxies like our Milky Way. But the Webb data suggests that massive galaxies were already in place just a few 100 million years after the Big Bang. This challenges the hierarchical merging scenario, implying that galaxies must have formed much faster and more efficiently than we thought possible. Second, black hole formation. Supermassive black holes are thought to form at the centers of galaxies, growing over time by accreting gas and merging with other black holes. The standard model suggests that this process takes billions of years. However, the Webb data reveals the existence of supermassive black holes at extremely early times, when the universe was only a fraction of its current age. This raises the question, how did these black holes grow so big so quickly? One possibility is that black holes can form directly from the collapse of massive gas clouds, bypassing the need for a seed black hole. This direct collapse scenario could potentially explain the rapid formation of supermassive black holes in the early universe. However, it requires very specific conditions, such as a high density of gas and a lack of angular momentum. It's unclear whether these conditions were common enough in the early universe to account for the abundance of early supermassive black holes observed by Webb. Another possibility is that the accretion rates of black holes in the early universe were much higher than we previously thought. If black holes could accrete gas at a super-Eddington rate, exceeding the theoretical limit, they could grow much faster than predicted by the standard model. However, it's unclear whether such high accretion rates are physically possible and what mechanisms could drive them. The implications extend beyond just galaxy and black hole formation. The existence of these early, massive structures could also have profound effects on the evolution of the intergalactic medium, the diffuse gas that fills the space between galaxies. The intense radiation from these galaxies and black holes could have ionized the intergalactic medium, heating it up and preventing it from collapsing to form new structures. This could have stunted the growth of smaller galaxies and influenced the distribution of matter in the universe. Furthermore, the compact nature of these early galaxies challenges our understanding of galaxy dynamics. The dense, stellar environment in these galaxies could have led to more frequent stellar collisions and mergers, which could have altered the distribution of stars and gas. It could also have influenced the formation of globular clusters, dense clusters of stars that orbit galaxies. These are some pretty complex questions, and it's clear that the James Webb Space Telescope is forcing us to confront some fundamental gaps in our understanding of the universe. The data is forcing cosmologists to go back to the drawing board and come up with new theories and models that can explain these unexpected observations. It's a challenging but also incredibly exciting time to be a cosmologist. And that's not all. There's a potential ripple effect that goes even deeper than just galaxy formation and black hole growth. It touches the very fabric of space-time and the fundamental constants of nature. This is where things get really interesting, and where the potential for a true paradigm shift emerges. December 2023. The astrophysics community started buzzing, not with excitement but with a growing sense of unease. The James Webb Space Telescope was sending back data that stubbornly refused to align with our existing cosmological models. We were seeing galaxies form far too quickly, far too early in the universe, and with far too much mass. How could structures so large and complex have assembled themselves in such a short amount of time? The established theories simply couldn't account for it. One of the biggest sticking points is the discrepancy between the observed abundance of massive galaxies in the early universe and the predictions of the lambda-CDM model, our current standard model of cosmology. This model does a pretty good job of explaining the large-scale structure of the universe, the cosmic microwave background, and the distribution of galaxies. But it struggles to explain these early JWST observations. The lambda-CDM model posits that the universe is dominated by dark energy, represented by the cosmological constant lambda, and cold dark matter, CDM. Dark matter, as you probably know, is a mysterious substance that makes up about 85% of the matter in the universe. It doesn't interact with light, which is why we can't see it directly, but we know it's there because of its gravitational effects on visible matter. It acts as a sort of scaffolding, providing the gravitational framework for galaxies and other structures to form. The problem is, the lambda-CDM model predicts a slower rate of structure formation in the early universe than what JWST is observing. The model suggests that it should have taken longer for enough dark matter to clump together and form the gravitational wells needed to seed the formation of galaxies. So, what could be going on? What could explain this mismatch between theory and observation? One possibility, and it's one that's gaining increasing attention, is that our understanding of dark matter itself is incomplete. Maybe dark matter isn't as cold and inert as we thought. Consider the possibility of warm dark matter, a variant of the dark matter hypothesis where dark matter particles are lighter and move faster than cold dark matter particles. This extra velocity could prevent dark matter from clumping together as efficiently, suppressing the formation of smaller structures and potentially leading to the formation of larger structures at an earlier time. Alternatively, perhaps dark matter interacts with itself or with other particles through forces other than gravity. These interactions could affect the way dark matter clumps together and influence the formation of galaxies. There are even more exotic possibilities, such as dark matter being composed of axions or other hypothetical particles with unique properties. The implications extend beyond just the nature of dark matter itself. If our understanding of dark matter is wrong, it could also affect our understanding of other fundamental aspects of cosmology, such as the expansion rate of the universe and the nature of dark energy. For instance, some theories propose a dynamic form of dark energy that evolves over time. If dark energy was stronger in the early universe, it could have accelerated the expansion rate and influenced the formation of structures. And then there's the possibility that our understanding of gravity itself needs to be revised. Einstein's theory of general relativity has been incredibly successful in explaining gravity on large scales, but it might break down under certain extreme conditions, such as in the very early universe or in regions with very high densities of dark matter. Modified Newtonian dynamics, MOND, is one alternative theory of gravity that proposes that gravity behaves differently at very low accelerations. MOND has had some success in explaining the rotation curves of galaxies without invoking dark matter, but it struggles to explain other cosmological observations. However, there are also more sophisticated modified gravity theories that attempt to reconcile MOND with general relativity and explain the full range of cosmological observations. These theories often involve adding new fields or modifying the geometry of spacetime. Scientists discovered that these early observations could point to a need to refine our understanding of the interplay between dark matter, dark energy, and gravity. The analysis continued. The question of whether these early massive galaxies are truly as abundant as JWST suggests is still an open one. It's possible that some of the observed galaxies are actually lensed by foreground objects, which could magnify their apparent brightness and make them appear more massive than they really are. Or it could be an issue with instrument calibration. But if the JWST observations hold up, they could force us to confront some pretty fundamental questions about our understanding of the universe. They could lead to a paradigm shift in cosmology, forcing us to rethink our theories of galaxy formation, dark matter, and gravity. This means we might need to consider entirely new physics. We expected a gradual build-up, small galaxies merging, slowly forming larger ones over billions of years. But the early universe, as seen by Webb, throws that picture out the window. Consider this. The standard model of galaxy formation relies heavily on dark matter halos. These halos are thought to be the gravitational scaffolding around which galaxies form. Smaller halos merge to create larger ones, and gas cools and condenses within these halos to form stars. This process is relatively slow and hierarchical, meaning smaller galaxies should form first, followed by larger ones. The problem? Webb is seeing fully formed massive galaxies way too early in the universe. Galaxies that shouldn't exist, according to our current understanding. It's like finding fully grown oak trees sprouting from the ground just days after the Big Bang. The timescale is completely off. How can these galaxies form so quickly? One possibility is that the dark matter halos formed much faster than we thought. Perhaps there were unusual fluctuations in the early universe that led to the rapid collapse of matter and the formation of these massive halos. But this would require a significant revision of our understanding of the nature of dark matter and its distribution in the early universe. Another possibility is that the process of star formation was much more efficient in the early universe. Perhaps the conditions were such that gas could cool and condense much more rapidly, leading to a burst of star formation that quickly transformed these galaxies into the massive objects we see today. However, this would require some fine-tuning of the parameters that govern star formation, and it's not clear what physical mechanisms could have caused this enhanced efficiency. The distribution of dark matter itself could be different than expected. Maybe it's more clumpy, more concentrated in certain regions, leading to faster galaxy formation in those areas. The observations don't align with our simulations, which are based on a relatively smooth distribution of dark matter. The implications extend beyond just galaxy formation. If these early massive galaxies are as abundant as JWST suggests, it could also have implications for our understanding of the rionization of the universe. Rionization is the process by which the neutral hydrogen gas in the early universe was ionized by the first stars and galaxies. This is a crucial epoch in the history of the universe, as it marked the end of the cosmic dark ages and the beginning of the universe as we know it today. If there were more massive galaxies in the early universe than we thought, they could have contributed significantly to the rionization process. This could help to explain why rionization happened earlier than expected, based on our current models. Here's what's wild. The early universe was a very different place than the universe we see today. It was denser, hotter, and more chaotic. The conditions were ripe for all sorts of exotic phenomena to occur, phenomena that we may not be able to fully understand based on our observations of the local universe. Perhaps there were new physical processes at play in the early universe that we are not yet aware of. Maybe there were new types of particles or new forces that influenced the formation of galaxies. Or maybe our understanding of the fundamental laws of physics is incomplete, and we need to revise our theories to account for the observations from JWST. This means we might need to consider entirely new physics. The universe is giving us hints that our current understanding is incomplete. It's challenging us to think outside the box and come up with new ideas. And that's exactly what scientists are doing. they're developing new models of galaxy formation, exploring new theories of dark matter and dark energy, and even questioning the fundamental laws of physics. These early galaxies might be much further away than we think. Redshift measurements are tricky, especially for very distant objects. A slight miscalculation in the redshift could lead to a significant overestimation of the distance and, therefore, the size and mass of the galaxy. Measurements showed it's possible that some of these objects aren't galaxies at all. They could be something else entirely, something we haven't even considered yet. Perhaps they are supermassive black holes surrounded by a cloud of gas, or some other exotic object that we don't yet have a name for. The data reveals that the problem isn't just the existence of these early massive galaxies, but also their properties. They seem to be much more metal-rich than expected. Metals, in astronomical terms, are elements heavier than hydrogen and helium. These elements are produced in the cores of stars and then released into the interstellar medium when the stars die. The fact that these early galaxies are so metal-rich suggests that they must have undergone several generations of star formation very quickly. This is difficult to explain with our current models, which predict that star formation should have been much slower in the early universe. Scientists discovered that the star formation rates in these early galaxies are also surprisingly high. They are forming stars at a much faster rate than galaxies of similar mass in the local universe. This suggests that there must have been a ready supply of gas available to fuel this rapid star formation. But where did this gas come from? And then there's the morphology of these galaxies. How do they look? Are they spiral galaxies like our Milky Way, or are they elliptical galaxies with a more rounded shape? The early observations from JWST suggest that these galaxies are surprisingly well-ordered, with well-defined disks and spiral arms. This is unexpected, as galaxies in the early universe were thought to be much more chaotic and irregular. The implications extend to the timeline of the universe itself. If galaxies formed much earlier and faster than we thought, it could compress the timeline of the early universe and change our understanding of how the universe evolved over time. This could have implications for our understanding of the formation of other structures in the universe, such as clusters of galaxies and the cosmic web. There's a massive problem with our current models. The James Webb Space Telescope is throwing a wrench into everything we thought we knew about the early universe. The sheer existence of these massive, mature galaxies so early in cosmic history is baffling enough, but when you start to dig into the details, that's when it gets really perplexing. So, what are the experts saying? What are the astrophysicists and cosmologists making of all this new data? Well, to put it mildly, they're rethinking things. Many are scrambling to revise their simulations and theoretical frameworks to accommodate these unexpected observations. It's not just a matter of tweaking a few parameters here and there. Some researchers are suggesting that we might need to fundamentally rewrite our understanding of galaxy formation. One of the biggest challenges is explaining how these galaxies manage to amass so much mass so quickly. Current models predict that galaxy formation should have been a much slower process, with galaxies gradually growing over billions of years. But the JWST observations suggest that at least some galaxies buck this trend, forming rapidly in the first few 100 million years after the Big Bang. Professor Garth Illingworth at the University of California, Santa Cruz, one of the leading astronomers in the field, stated that the new JWST data is much more surprising than many people anticipated. He emphasized the need for new theoretical models to explain the rapid formation of these early galaxies. Another prominent astrophysicist, Dr. Rebecca Larson from the University of Texas at Austin, commented that the high metal content in these early galaxies is particularly puzzling. It suggests that these galaxies underwent intense bursts of star formation very early on, which is difficult to reconcile with our current understanding of the early universe, she explained. The implications extend to our understanding of dark matter. Dark matter is thought to play a crucial role in the formation of galaxies, providing the gravitational scaffolding that allows them to coalesce. But if galaxies formed much earlier and faster than we thought, it could mean that dark matter behaved differently in the early universe than it does today. Some scientists are even suggesting that we might need to revise our understanding of the fundamental laws of physics to account for these observations. This is a more radical suggestion, but it's not entirely out of the question. After all, our current understanding of physics is based on observations made in the local universe. It's possible that the laws of physics were slightly different in the early universe, or that there are new physical phenomena that we haven't yet discovered. Here's what's wild. The James Webb Space Telescope is still in its early stages of operation. It has only been observing the universe for a little over a year, and it has already made a number of groundbreaking discoveries. As it continues to collect more data, it's likely to uncover even more surprises, which could further challenge our understanding of the universe. The situation isn't just generating excitement, it's also creating a sense of urgency. Researchers are racing to analyze the new JWST data and develop new theoretical models to explain the observations. There's a real sense that we're on the cusp of a major breakthrough in our understanding of the universe. Consider this: if our current models of galaxy formation are indeed fundamentally flawed, it could have implications for our understanding of other areas of astrophysics and cosmology. It could affect our understanding of the formation of black holes, the evolution of the cosmic web, and the nature of dark energy. The analysis continued. Scientists began looking at the specific types of stars that were forming in these early galaxies. The initial results were even more unexpected. The stars seemed to be unusually massive and hot, burning through their fuel at a much faster rate than stars in the local universe. This would explain the high metal content of these galaxies, as these massive stars would have produced and released large amounts of heavy elements. This poses yet another challenge. How did these galaxies manage to form so many massive stars so early in their history? Current models suggest that the conditions in the early universe should have been less conducive to the formation of massive stars. One possibility is that the early universe was more turbulent than we thought, with more frequent collisions between gas clouds. These collisions could have compressed the gas, triggering the formation of massive stars. Measurements showed that the gas in these early galaxies was also much denser than expected. This would have made it easier for stars to form, as the gas would have been more likely to collapse under its own gravity. Another idea is that the early universe was enriched with a higher concentration of heavy elements than we previously thought. This could have cooled the gas more efficiently, allowing it to collapse and form stars more easily. And then, scientists discovered that these early galaxies are often found in close proximity to each other, forming what are known as galaxy clusters. This suggests that these galaxies may have influenced each other's evolution, perhaps through gravitational interactions or by exchanging gas and stars. The implications extend to our understanding of the formation of supermassive black holes. These behemoths, which reside at the centers of most galaxies, are thought to play a key role in regulating galaxy formation. But if galaxies formed much earlier and faster than we thought, it could mean that supermassive black holes also formed much earlier and faster than we thought. One possibility is that these black holes formed directly from the collapse of massive gas clouds in the early universe. Another idea is that they formed from the mergers of smaller black holes. Either way, the discovery of these early massive galaxies is forcing scientists to rethink their theories about the formation of supermassive black holes. Webb's unprecedented glimpse into the early universe isn't just about pushing back the cosmic timeline, it's about what it's seeing. These galaxies are far too mature, far too massive, and far too chemically evolved for their supposed age. It's like finding a fully grown oak tree sprouting from the ground just days after a forest fire. Doesn't add up. Consider the implications. Our entire understanding of galaxy formation is built on a hierarchical model. Small clumps of matter gradually merge over billions of years to form larger structures. But the JWST observations suggest that at least some galaxies skip this gradual process and somehow assembled themselves incredibly quickly. This presents a major challenge to cosmologists. If galaxies can form so rapidly, what are the mechanisms that drive this rapid formation? What role do dark matter halos play? How do these early galaxies manage to avoid being disrupted by mergers and tidal forces? The current models struggle to explain the sheer abundance of massive galaxies in the early universe. Simulations consistently underestimate the number of these objects, suggesting that we are missing something fundamental in our understanding of how galaxies form. One possibility is that the initial conditions in the early universe were different than we thought. Perhaps there were larger density fluctuations in the primordial soup of matter, which allowed some regions to collapse more quickly and form massive galaxies. Another idea is that the laws of physics themselves may have been slightly different in the early universe. This is a more radical suggestion, but it could explain why the early universe seems to defy our current understanding of physics. Let's examine the chemical composition of these early galaxies. Scientists found unexpectedly high levels of heavy elements such as carbon, oxygen, and nitrogen. These elements are forged in the cores of stars and then released into the interstellar medium through supernova explosions. The presence of these heavy elements in such young galaxies implies that they must have already gone through several generations of star formation. This is difficult to reconcile with the short amount of time that has elapsed since the Big Bang. How did these galaxies manage to form so many stars and produce so many heavy elements in such a short period? The conventional explanation is that the early universe was characterized by a higher rate of star formation than the present-day universe. This would have allowed galaxies to quickly build up their stellar populations and produce heavy elements. But the JWST observations suggest that the rate of star formation in these early galaxies may have been even higher than we previously thought. This implies that the conditions in the early universe must have been even more extreme than our current models predict. Scientists discovered that these early galaxies are often much more compact than their modern counterparts. This means that their stars are packed much more closely together, which could have important consequences for their evolution. A higher stellar density would have increased the rate of stellar collisions and mergers, leading to the formation of even more massive stars and black holes. It would have also made it easier for gas to collapse and form new stars. Furthermore, the compact nature of these early galaxies could have made them more vulnerable to feedback from supermassive black holes. These black holes can release vast amounts of energy, which can heat and expel gas from the galaxy, shutting down star formation. The implications extend to the formation of globular clusters. These dense clusters of stars are found in the halos of most galaxies, and their origin is still a matter of debate. One theory is that they formed in the early universe, alongside the first galaxies. If galaxies formed much earlier and faster than we thought, it could mean that globular clusters also formed much earlier and faster than we thought. This could help to explain why globular clusters are so old and metal-poor. Meanwhile, JWST is also providing new insights into the nature of dark matter. This mysterious substance makes up about 85% of the matter in the universe, but its exact nature is still unknown. One possibility is that it consists of weakly interacting massive particles, WIMPs. If dark matter is made up of WIMPs, it should interact with ordinary matter through the weak nuclear force. This interaction could produce detectable signals, such as gamma rays or neutrinos. The analysis continued. Scientists have been searching for these signals for decades, but so far, they have found no conclusive evidence for WIMPs. However, the JWST observations could provide new clues about the nature of dark matter. By studying the distribution of galaxies in the early universe, JWST can map out the distribution of dark matter on large scales. This could help to constrain the properties of dark matter and narrow down the search for WIMP signals. Here's what's wild. The JWST data is also challenging our understanding of the Rhionization epoch. This is the period in the early universe when the first stars and galaxies began to ionize the neutral hydrogen gas that filled the cosmos. This process is thought to have played a key role in shaping the evolution of the universe. It is believed that ultraviolet radiation from these early galaxies ionized the hydrogen gas, making the universe transparent to light. The timing and duration of the Rhionization epoch are still poorly understood. Current estimates suggest that it began about 13 billion years ago and lasted for several 100 million years. However, the JWST observations suggest that the Rhionization epoch may have occurred earlier and faster than we previously thought. This could mean that the first stars and galaxies were more abundant and luminous than our current models predict. Scientists discovered that these early galaxies are often surrounded by large halos of ionized gas. These halos are thought to be produced by the intense radiation emitted by the galaxies. The size and shape of these halos can provide information about the properties of the galaxies and the conditions in the surrounding intergalactic medium. The JWST observations are providing unprecedented details about these halos, allowing scientists to study the Rhionization epoch in greater detail. The implications extend to the search for extraterrestrial life. If galaxies formed much earlier and faster than we thought, it could mean that life also emerged much earlier in the universe. This would increase the chances of finding extraterrestrial life, both in our own galaxy and in other galaxies. And then there's the question of whether the universe is even expanding at the rate we thought. The Hubble constant, which measures the expansion rate, has been a source of controversy in recent years, with different methods of measuring it yielding different results. Perhaps JWST can shed new light on this discrepancy. This means every simulation needs rewriting, potentially. All those carefully constructed models of the universe's evolution? They might be fundamentally flawed. It's not just tweaking a few parameters, it's rethinking the entire framework. And the lambda CDM model, our current standard model of cosmology, well, it's facing a serious challenge. Lambda CDM assumes a universe dominated by cold, dark matter and a cosmological constant, lambda, representing dark energy. It's been remarkably successful in explaining many observed features of the cosmos, from the cosmic microwave background to the large-scale structure of galaxies. But the JWST findings, specifically the abundance of massive mature galaxies in the early universe, are creating tension with this model. These galaxies seem to have formed far too quickly and are far too massive to fit comfortably within the lambda CDM paradigm. So, what are the alternatives? What other theoretical frameworks might be able to accommodate these new observations? One possibility is modified Newtonian dynamics, or MOND. MOND proposes that our understanding of gravity is incomplete and that at very low accelerations, gravity deviates from the predictions of Newtonian physics and general relativity. This modification could potentially explain the observed rotation curves of galaxies without invoking dark matter. While MOND has had some success in explaining galactic dynamics, it has struggled to account for the large-scale structure of the universe and the cosmic microwave background. However, some researchers are exploring modified versions of MOND that could potentially address these shortcomings. Another area of active research involves alternative models of dark matter. The standard lambda CDM model assumes that dark matter is cold, meaning that it consists of particles that move slowly compared to the speed of light. However, other possibilities exist, such as warm dark matter, or even fuzzy dark matter, which consists of extremely light particles that exhibit wave-like behavior. These alternative dark matter models could potentially affect the formation of galaxies in the early universe and might be able to explain the JWST observations. Then there's the possibility that our understanding of dark energy is incomplete. The cosmological constant lambda is the simplest explanation for dark energy, but it also suffers from a major theoretical problem. Its predicted value is vastly larger than what we observe. This discrepancy has led to the exploration of alternative dark energy models, such as quintessence, which proposes that dark energy is a dynamic field that evolves over time. These models could potentially affect the expansion rate of the universe and the formation of large-scale structures. And it's not just about tweaking existing models. Some physicists are exploring entirely new theoretical frameworks that could potentially revolutionize our understanding of the universe. These include ideas like modified gravity theories, which attempt to modify Einstein's theory of general relativity to account for the observed accelerated expansion of the universe, and even theories that propose the existence of extra dimensions. Consider, for example, the work of Dr. Nyayesh Afshori at the University of Waterloo, who has suggested that the universe might be the 3D surface of a 4D black hole. It's a radical idea, but it's one that attempts to address the inconsistencies between the observed Hubble constant and the predictions of lambda CDM. The analysis continued. There's also the possibility of interactions between dark matter and dark energy. Currently, these are treated as separate entities, but what if they influence each other? Some models propose an exchange of energy between these components, which could alter the expansion history of the universe and affect structure formation. It is not a widely accepted hypothesis, but it's being looked at by some groups. It's also important to consider that our understanding of galaxy formation itself might be incomplete. Current models rely on complex simulations that incorporate a variety of physical processes, such as gravity, gas dynamics, and star formation. However, these simulations are computationally expensive and often require simplifying assumptions. It's possible that some important physical processes are not being adequately captured in these simulations, which could lead to inaccurate predictions about the formation of galaxies in the early universe. Furthermore, feedback from supermassive black holes could play a more significant role than previously thought. These black holes, lurking at the centers of galaxies, can release enormous amounts of energy that can affect the surrounding gas and star formation. If this feedback is more efficient in the early universe than we currently assume, it could potentially explain the rapid formation of massive galaxies. Scientists discovered that the JWST data presents an opportunity to refine our understanding of the initial mass function, or IMF. The IMF describes the distribution of stellar masses in a newly formed population of stars. If the IMF in the early universe was different from what we observe today, with a higher proportion of massive stars, it could potentially explain the abundance of bright galaxies seen by JWST. The implications extend to the fundamental constants of nature. Are they truly constant? Some theories suggest that fundamental constants such as the fine structure constant or the gravitational constant might have varied slightly over cosmic time. While there's no direct evidence for this, such variations could have significant effects on the formation of stars and galaxies in the early universe. It is a long shot, but physicists can't rule it out. And then there's the anthropic principle, which suggests that the universe's properties are fine-tuned for the existence of life. If the universe were even slightly different, life as we know it would not be possible. While the anthropic principle is controversial, it raises the possibility that our observations of the universe are biased by the fact that we exist to observe them. Perhaps the early formation of massive galaxies is a necessary condition for the emergence of life, and we are simply observing a universe that is conducive to our existence. It is not a popular idea, but it can't be discounted. Measurements showed that the JWST observations are pushing us to think outside the box and to consider radical, new ideas about the nature of the universe. It's a reminder that our current understanding of cosmology is still incomplete, and that there are many mysteries yet to be solved. Here's what's wild. This isn't just about cosmology, it's about fundamental physics. If our understanding of the universe is wrong, it means that our understanding of the laws of nature is also incomplete. This could have profound implications for many areas of physics, from particle physics to quantum gravity. And then there's the sheer hubris of it all. We, a tiny blip on the cosmic timeline, are attempting to understand the entirety of existence. Maybe, just maybe, the universe is far stranger and more complex than we can possibly imagine. And perhaps the JWST is giving us a glimpse of that reality. Meanwhile, back on Earth, the theoretical physicists have a lot of work to do. You've been told the universe is expanding at an accelerating rate. It's practically textbook knowledge at this point, but what if that acceleration isn't quite what we think it is? What if it's not constant? This is where the JWST observations are really stirring the pot. The accelerating expansion of the universe is based on observations of distant supernova, Type 1a supernovae to be specific. These are used as standard candles because they have a known intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance. Comparing this distance to their redshift, how much their light has been stretched by the expansion of the universe, gives a measure of the expansion rate at different points in cosmic history. However, this relies on the assumption that Type 1a supernovae are truly standard candles, that their intrinsic brightness is always the same. What if supernovae in the early universe were slightly different? What if their brightness evolved over time? If that's the case, our measurements of cosmic distances would be off, and our conclusions about the accelerating expansion of the universe might need revision. It's a subtle point, but crucial. Even a small change in the intrinsic brightness of supernovae could have a significant impact on our understanding of dark energy. Dark energy is the mysterious force that's thought to be driving the accelerating expansion. If the expansion isn't accelerating as much as we thought, we'd need less dark energy to explain it. It could even vanish entirely as a necessity of our model. The JWST is now peering back at some of the most distant supernovae ever observed, and it's doing so with unprecedented precision. This new data will allow astronomers to test whether Type 1a supernovae really are standard candles or if they evolve over cosmic time. If the JWST finds evidence of evolution, it could rewrite our understanding of dark energy and the fate of the universe. Consider this. The evidence for dark energy is almost entirely indirect. We infer its existence from the observed expansion rate of the universe. We don't directly detect it. This is why some scientists are skeptical and are exploring alternative explanations for the accelerating expansion. One such explanation is modified gravity. This idea suggests that our understanding of gravity, as described by Einstein's theory of general relativity, might be incomplete. Perhaps gravity behaves differently on very large scales than we currently understand. If so, this could mimic the effects of dark energy, causing the universe to expand at an accelerating rate without the need for any mysterious new force. Modified gravity theories are complex and still under development, but they offer a compelling alternative to dark energy, and the JWST observations could provide crucial tests for these theories. By mapping the distribution of galaxies and dark matter in the early universe, the JWST can probe the behavior of gravity on the largest scales. If the JWST data is inconsistent with general relativity, it would provide strong support for modified gravity. The implications extend beyond cosmology. If dark energy doesn't exist, or if gravity is different than we thought, it would have profound consequences for our understanding of fundamental physics. Our current models of particle physics and the structure of space-time are based on the assumption that general relativity is correct. If it's not, we may need to rethink everything we know about the laws of nature. The current understanding of dark energy relies heavily on the cosmological constant. The cosmological constant is a term in Einstein's equations that represents the energy density of empty space. It's thought to be responsible for the accelerating expansion of the universe. However, the observed value of the cosmological constant is incredibly small, much smaller than what theoretical physics predicts. This discrepancy is known as the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. If the JWST observations lead us to abandon the cosmological constant, it could solve this problem and open up new avenues for theoretical research. It's not just about tweaking our models, it's about potentially overhauling them. And then there's the possibility that the universe isn't homogeneous and isotropic on the larger scales. The cosmological principle states that the universe looks the same in all directions and at all locations. This principle is a cornerstone of modern cosmology. But what if it's wrong? What if the universe has large-scale structures such as voids and superclusters that affect the expansion rate in different regions? If that's the case, our measurements of the average expansion rate might be misleading. We might be living in a region of the universe that's expanding at a different rate than the universe as a whole. The JWST can help test the cosmological principle by mapping the distribution of galaxies and dark matter on the largest scales. If the JWST finds evidence of significant inhomogeneities, it could challenge our fundamental assumptions about the nature of the universe. This means reconsidering the very foundations upon which our theories are built. It's a daunting task, but it's also incredibly exciting. The JWST is pushing us to confront some of the deepest mysteries in science and to question everything we thought we knew. Meanwhile, theorists are exploring a range of exotic possibilities. From axions to quintessence, the theoretical landscape is filled with potential candidates for dark matter and dark energy. The JWST observations will provide crucial data to test these theories and to guide the search for new physics. Here's what's wild. The JWST is still in its early stages of operation. It's already challenging our understanding of the universe in profound ways. Imagine what it will discover in the years to come. It's not unreasonable to suggest that we are on the verge of a scientific revolution. The JWST is not just a telescope. It's a time machine allowing us to peer back into the early universe and to witness the events that shaped our cosmos. And it may just rewrite the textbooks in the process. Our current understanding of the universe might be fundamentally flawed. That's a bold statement, I know. But the data coming from the James Webb Space Telescope is increasingly difficult to reconcile with our existing cosmological models. We're not talking about minor tweaks here, we're talking about potentially rewriting the textbooks. So, what does it all mean? Well, first it means we need to be humble. For decades, we've operated under certain assumptions about the universe, its age, its composition, its expansion rate. The JWST is showing us that some, if not all, of those assumptions may be incorrect. It's a cosmic reality check. Consider the implications for the Hubble constant. If the discrepancy between local and early universe measurements persists, it suggests there's something fundamentally wrong with our understanding of the expansion history of the universe. This could point to new physics beyond the standard model, such as new particles or interactions that affect the expansion rate. And then there's the issue of dark matter and dark energy. These mysterious entities make up about 95% of the universe, yet we know almost nothing about them. The JWST's observations of early galaxies and the cosmic web can help us map the distribution of dark matter and to probe the nature of dark energy. The telescope can also search for axions, hypothetical particles that are considered leading candidates for dark matter. Axions are predicted to interact very weakly with light, which means they could be detected through their subtle effects on the polarization of light from distant galaxies. Furthermore, JWST can study the properties of dark energy by measuring the expansion rate of the universe at different epochs. By observing distant supernovae and quasars, the telescope can precisely determine the distances and redshifts of these objects, which can then be used to constrain the equation of state of dark energy. It's entirely possible that dark matter and dark energy aren't what we think they are. They could be manifestations of something even more exotic, something we haven't even conceived of yet. The JWST is giving us the tools to explore these possibilities. Think about the implications for our understanding of galaxy formation. The JWST is revealing that galaxies in the early universe were far more massive and mature than we previously thought. This challenges our models of how galaxies form and evolve over cosmic time. If galaxies formed much faster than expected, it suggests that our understanding of the processes that drive galaxy formation is incomplete. This could mean that we're missing crucial ingredients in our simulations, such as the role of supermassive black holes or the effects of feedback from star formation. Measurements showed that the JWST is also providing new insights into the formation of the first stars and black holes. By observing the most distant galaxies, the telescope can probe the conditions that existed in the early universe, when the first stars and black holes were forming. This can help us understand how these objects influence the evolution of the universe and the formation of galaxies. What about the potential for completely new physics? The JWST is pushing us to the limits of our current knowledge. It's showing us that the universe is far more complex and mysterious than we ever imagined. This opens up the possibility that there are entirely new laws of physics waiting to be discovered. Perhaps there are new particles or forces that we haven't yet detected. Perhaps our understanding of gravity is incomplete. Or perhaps the universe is governed by principles that we simply haven't grasped yet. The implications extend beyond just astrophysics and cosmology. They touch on fundamental questions about the nature of reality, the origin of the universe, and our place in the cosmos. The JWST is forcing us to confront these questions in a new and profound way. And then there's the philosophical dimension. For centuries, science has been driven by the quest for a complete and consistent understanding of the universe. The JWST is showing us that this quest may be more challenging than we ever realized. It's a reminder that our knowledge is always provisional and that we must be open to the possibility that our current theories are incomplete or even incorrect. This doesn't mean our existing theories are useless. They've been incredibly successful in explaining many aspects of the universe. But it does mean we need to be willing to revise or even abandon them if they're inconsistent with the data. It's like we've been trying to assemble a puzzle with some of the pieces missing. The JWST is providing us with new pieces, but they don't always fit into the picture we had in mind. This means we need to rethink how the puzzle fits together. The analysis continued. The JWST is not just a scientific instrument, it's a cultural artifact. It represents the culmination of decades of human ingenuity and collaboration. It's a testament to our ability to push the boundaries of knowledge and to explore the universe in ever greater detail. Here's what's wild. The JWST is also a source of inspiration. It's showing us the beauty and wonder of the cosmos, reminding us that we are part of something much larger than ourselves. It can inspire future generations of scientists, engineers, and explorers to continue pushing the boundaries of knowledge and to seek answers to the deepest questions about the universe. It's a symbol of hope and possibility. The JWST is challenging us to think bigger, to question our assumptions, and to embrace the unknown. It's a journey into the heart of the cosmos, and it's a journey that will transform our understanding of the universe and our place within it. It's an exciting time to be alive. We are witnessing a scientific revolution unfold before our very eyes, and the JWST is leading the way. The implications extend far beyond what we can even imagine right now. It's truly a different universe than we thought. 600 scientists are about to have their work completely overturned. That's the scale of what the James Webb Space Telescope is hinting at, regarding the future of cosmology. It's not just tweaking the existing models, it's potentially rebuilding them from the ground up. Cosmology, at its heart, seeks to understand the origin, evolution, and ultimate fate of the universe. For decades, we've relied on the lambda-CDM model, a framework that incorporates dark energy, lambda, and cold dark matter, CDM, as the dominant components shaping the cosmos. It's been remarkably successful, explaining everything from the cosmic microwave background to the large-scale structure of galaxies. But the JWST's observations of early galaxies are throwing a wrench into this well-oiled machine. These galaxies appear far too massive and mature for their age, based on our current understanding of how quickly galaxies should form in the early universe. If confirmed, this discrepancy could necessitate a fundamental revision of our cosmological models. So, what does this mean for the future of cosmology? First, it means we need to be open to the possibility that our current understanding of dark matter and dark energy is incomplete or even incorrect. These mysterious entities make up about 95% of the universe, yet we know almost nothing about their true nature. The JWST's findings could provide clues to unraveling these cosmic enigmas. Perhaps dark matter is not as cold as we thought, meaning it interacts more strongly with ordinary matter and influences galaxy formation differently. Or maybe dark energy is not a constant force, but rather a dynamic field that evolves over time. These are just a few of the possibilities that cosmologists are now exploring. Second, the JWST's observations could lead to new theories of gravity that go beyond Einstein's general relativity. While general relativity has been incredibly successful in describing gravity on a large scale, it may break down in the extreme conditions of the early universe. Some physicists are exploring alternative theories of gravity, such as modified Newtonian dynamics, MOND, or tensor vector scalar gravity, TEVES, which could potentially explain the formation of massive galaxies in the early universe without invoking dark matter. Third, the JWST's findings could revolutionize our understanding of galaxy formation and evolution. Our current models assume that galaxies grow gradually over time through mergers and accretion of smaller objects. But the JWST's observations suggest that galaxies may have formed much more rapidly in the early universe than we previously thought. This could mean that we need to revise our understanding of the processes that govern star formation, black hole growth, and the interplay between galaxies and their environment. The implications extend to our understanding of the universe's age, too. If galaxies formed far more rapidly than previously imagined, it might suggest that the universe is actually older than the currently accepted 13.8 billion years. This, of course, would have profound implications for our understanding of the Big Bang and the subsequent evolution of the cosmos. The future of cosmology also hinges on combining the JWST's observations with data from other telescopes and experiments. For example, the European Space Agency's Euclid mission, scheduled for launch in 2023, will map the distribution of galaxies and dark matter over a large portion of the sky. This data, combined with the JWST's detailed observations of individual galaxies, could provide a more complete picture of the universe's large-scale structure and its evolution. Furthermore, ground-based telescopes like the Vera C. Rubin Observatory, currently under construction in Chile, will conduct a 10-year survey of the southern sky, providing a wealth of data on the distribution of galaxies, supernova, and other cosmic objects. This data will complement the JWST's observations and help us to refine our cosmological models. The future also depends on the next generation of cosmologists, astrophysicists, and data scientists who are willing to challenge the status quo and embrace new ideas. The JWST's findings are a call to action for young researchers to push the boundaries of knowledge and to explore the unknown with curiosity and creativity. The JWST is not just providing us with new data, it's also providing us with new tools for understanding the universe. The telescope's advanced spectrographs allow us to analyze the light from distant galaxies in unprecedented detail, revealing their chemical composition, temperature, and velocity. This information can be used to test our models of galaxy formation and evolution. The telescope's high-resolution cameras also allow us to study the morphology of galaxies in exquisite detail, revealing the presence of spiral arms, bars, and other structural features that can provide clues to their formation history. It's easy to get caught up in the technical details, but it's important to remember that the JWST's discoveries have profound implications for our understanding of our place in the universe. If our current cosmological models are indeed incomplete or incorrect, it means that our understanding of the fundamental laws of nature is also incomplete. This could lead to new discoveries in physics that have far-reaching consequences for our understanding of the world around us. It could also lead to new technologies that are based on these new discoveries. The JWST is showing us that the universe is far more complex and mysterious than we ever imagined. It's a reminder that our knowledge is always provisional and that we must be open to the possibility that our current theories are incomplete or even incorrect. It's a humbling realization, but it's also an exciting one. The JWST is challenging us to think bigger, to question our assumptions, and to embrace the unknown. It's a journey into the heart of the cosmos, and it's a journey that will transform our understanding of the universe and our place within it. And then there's the philosophical side of all this. Does the fact that our understanding of the universe is constantly evolving diminish the value of what we currently know? I don't think so. Each new discovery builds upon the foundations laid by previous generations of scientists, adding another layer to our understanding of the cosmos. The JWST is not just a scientific instrument, it's a cultural artifact. It represents the culmination of decades of human ingenuity and collaboration. It's a testament to our ability to push the boundaries of knowledge and to explore the universe in ever greater detail. It's also a source of inspiration, showing us the beauty and wonder of the cosmos, reminding us that we are part of something much larger than ourselves. The implications of the JWST's findings are far-reaching. They touch upon fundamental questions about the nature of dark matter and dark energy, the validity of general relativity, and the processes that govern galaxy formation and evolution. They challenge us to rethink our assumptions and to embrace new ideas. Ultimately, the future of cosmology is uncertain, but one thing is clear. The James Webb Space Telescope has opened a new window on the universe, and it's up to us to explore it. What if the universe isn't just expanding, but also evolving in ways we haven't even conceived of yet? The JWST data is poking holes in some of our most cherished cosmological assumptions. It's like we've been looking at a map of the world that's suddenly revealed to be wildly inaccurate. The implications extend beyond just tweaking a few parameters in our existing models. We're talking about the potential for fundamentally new physics, new types of particles, new forces that we haven't even begun to imagine. It's not just about refining our measurements, it's about potentially rewriting the textbooks. Consider dark matter, for instance. We know it's there because without it, galaxies wouldn't spin the way they do. But what is it? We've spent decades searching for weakly interacting massive particles, WIMPs, the leading candidate for dark matter. But the searches have come up empty. Could it be that our assumptions about the nature of dark matter are wrong? Could it be something far more exotic, something that interacts with ordinary matter in ways we don't yet understand? The JWST data could provide clues. By observing the distribution of dark matter in the early universe, we might be able to infer its properties and its interactions. This could lead to new experiments, new searches, and ultimately, a breakthrough in our understanding of this mysterious substance. And then there's dark energy, the even more mysterious force that's driving the accelerated expansion of the universe. We know even less about dark energy than we do about dark matter. Is it a cosmological constant, a fundamental property of space itself? Or is it something else, something that varies with time and space? The JWST can help us probe the nature of dark energy by measuring the distances to faraway galaxies with unprecedented precision. This could reveal subtle variations in the expansion rate of the universe, which could in turn provide clues about the properties of dark energy. It's easy to get caught up in the technical details, but it's important to remember the big picture. We're talking about the fundamental nature of reality. We're talking about the origins of the universe, its evolution, and its ultimate fate. These are questions that have fascinated humanity for millennia. The JWST is giving us the tools to address these questions with unprecedented precision. It's a journey into the unknown, a voyage of discovery that will challenge our assumptions and expand our horizons. It's a reminder that the universe is far more complex and mysterious than we ever imagined. And this isn't just some abstract academic exercise. A deeper understanding of the universe could have profound implications for our technology and our society. For example, a better understanding of dark energy could lead to new ways of harnessing energy, perhaps even tapping into the vacuum energy of space itself. Imagine a future where energy is abundant and clean, where we can travel to the stars, where we can manipulate the very fabric of space-time. It sounds like science fiction, but it's not beyond the realm of possibility. The JWST is opening up new avenues of research that could lead to these kinds of breakthroughs. The analysis continued. Scientists discovered that some of the earliest galaxies appear to be far more massive and more evolved than our current models predict. These galaxies are teeming with heavy elements, elements that should have taken billions of years to form in stars. Yet here they are, in galaxies that are only a few 100 million years old. How is this possible? One explanation is that our understanding of star formation in the early universe is incomplete. Perhaps stars formed much faster and more efficiently than we thought. Or perhaps there were other processes at work, processes that we haven't yet discovered. Another possibility is that our understanding of galaxy formation is flawed. Perhaps galaxies merged together much earlier and more frequently than our models predict. This could have led to the rapid buildup of heavy elements in these early galaxies. Whatever the explanation, it's clear that the JWST is challenging our fundamental assumptions about the formation and evolution of galaxies. It's forcing us to rethink our models and to consider new possibilities. The implications extend to our understanding of the cosmic microwave background, the afterglow of the Big Bang. The cosmic microwave background is remarkably uniform, but it does contain tiny fluctuations in temperature. These fluctuations are thought to be the seeds of all the structure in the universe, the seeds that grew into galaxies, stars, and planets. However, the JWST data suggests that these fluctuations may be more complex than we thought. There are hints of correlations between these fluctuations and the distribution of galaxies in the early universe. This could mean that our understanding of the physics of the early universe is incomplete. The data reveals that we're only beginning to scratch the surface of understanding the universe. It's a vast and complex place, filled with mysteries that we haven't even begun to solve. But with the JWST, we have a powerful new tool to explore these mysteries. It's a journey that will take us to the edge of our knowledge, and perhaps beyond. The future is unwritten, and the universe is still unfolding. If you're excited about this journey, consider subscribing for more deep dives into the cosmos.